section, we're going to combine all the different methods in order to complete factoring process and finding x-intercepts together in this one place. And the tricky part about doing this is now that you're not given a particular method for factoring, you want to find what's the easiest way to go through the factoring process in order to find the x-intercepts using zero product principle. And throughout this process, with this set of problems, I'm going to share my strategies of how to recognize some of the patterns quickly and how it helps me think about what are the special forms that I can use or whether there are any easier methods for factoring than others. And the goal for us is to recognize these patterns eventually yourself. And once you recognize a pattern quickly yourself, factoring process becomes much faster when you have a mixed bag of problems. Now, looking at just a set of problems, there are a few things I would notice right away. The first thing we can see is if you take a minute to look at parts A through H, we see that most of the functions are trinomials, meaning there are 3 terms in them, and some of the functions, however, like part G, has 4 terms. And whenever we have 4 terms, this is usually a clear sign for us to use factor by grouping over here. Certainly you can go through and combine the like terms, then do the AC method, but we know the goal for AC method is eventually break it down to factor by grouping. So if you already have 4 terms, that's basically a sign to tells us that we want to do factor by grouping right away. And then the other thing we want to recognize over here is we have some terms with only, or some expressions with only 2 terms, which are binomials. And the only binomials we can factor other than the greatest common factor we can use is to use some special form. And whenever you see binomials, I want you to think about GCF and special forms to consider, because otherwise our AC methods or our trinomial with a leading coefficient being 1 doesn't really work over here. And this has to be a special form as well. And we can even narrow this down a little bit over here because we have 2 terms subtracted from each other. The only special form that would fit this description is our difference of squares over here. So if you see that right away, I want you to think about, can you see these 2 as possible candidates for differences of squares? Difference of squares. And if you recognize its difference of squares, then we can just directly use the formula we know about difference of squares right away. But again, these are the first things I recognize. So when we have only 2 terms, that's going to be a special form. That's the only type of binomial we know how to factor. When we have 4 terms, that's factor by grouping. So these are the things I would recognize first. And if we have 4 terms, we would have factor by grouping. Now for the trinomials, these are the ones that we want to look a little bit more closely and see whether there are any special patterns we recognize, whether it's a special form or leading coefficient being 1, and worst case we'll have to use the AC method, which is a lengthiest method, but we have already known or practiced with this already, so just basically buckle down and get started on these problems. It might take a little bit, but we know that that's the last resort. So we're not wasting or spending extra time on something that doesn't require that much effort. So now that I've already said we have factor by grouping for part B, I'm going to go ahead and start from that question. So in part B, we recognize we have 4 terms, and first thing I always check for factoring is always GCF. And always check GCF first. It's very easy to forget. It's a nice little thing to do, but because we've done it earlier on, it's easy to overlook that strategy, but it totally makes a big difference. And looking at the entire expression of g of x in part B, I don't see any GCF across the board, so I'm ready to use the other factoring methods. And here to go through factor by grouping, I'm going to group the first 2 terms together, last 2 terms together, connected by addition over here. And I always like to do this just so I don't have to worry about the leading terms being negative or things like that. That can be taken care of by taking out the GCF from each group later. And that way I don't need to worry about changing signs right away. And once I do this, the first group, 2x squared minus 8x, we have a common factor of 2 being the coefficient, and also the variable, the lowest degree of the variable is x, so we can factor that out as well. Once we do so, we're left with x minus 4 here. And then for the second group, because the leading term is positive in the second group, so I'm just going to keep the plus sign as is. And if we look at the GCF in the second group, we can factor out a factor of 3, and that leaves us with x minus 4. Now to put everything together, both contain x minus 4, so we can have x minus 4 times 2x from the first group, positive 3 from the second group. And that's how we can get the factored form. Once we have the factored by group over here, we can identify x minus 4 equal to 0 or 2x plus 3 equal to 0. And here we get x equal to 4, or x is equal to negative 3 over 2. Take your time to solve the equation. We have done it a bunch of times, so I'm just speeding up the process and list out the answers right away. And these are the two x coordinates of the x-intercept. So we have 4, 0 and negative 3, half 0 being our answers for x-intercepts. And this is with 4 terms. Now I also said if we only had 2 terms, these are special forms, and in particular they're difference of squares in this case because we have a minus, and we recognize that they're both square terms. They're both quadratic functions over here. And in this case, if we want to go ahead and factor that, remember for difference of squares, we're looking for a squared minus b squared as the form. And here that means our first term needs to be a squared, so if a squared equals 9, that means a equals 3. And similarly, if b squared equals 36x squared, to find b, I can take the square root of both sides, and square root of 36 becomes 6, square root of x squared becomes x. And now to put it all together, a squared minus b squared equals a plus b times a minus b. And once you recognize the special form, make sure you know how to factor out the special form as well. So that tells me L of x is equal to a plus b, which is 3 plus 6x times 3 minus 6x over here. And once I've done this, I notice that I've jumped the gun here for not checking the GCF first. And this is another thing you should be able to recognize. Your fully factored form shouldn't contain any GCF in each factor. And as I see, I totally do over here. In the first parentheses, I have that 3 that I didn't factor out over here. So to fix my mistake, I will have to factor out the 3 over here from the first parentheses, and that would leave me with 1 plus 2x from the first parentheses. And now also recognize from the second parentheses, the second factor, I still have a factor of 3 to take out. So I would have to take out the 3 again, and then that leaves me with 1 minus 2x over here. And now to put everything together, 3 times 3 can be combined because for multiplication the order doesn't matter, and we would have 9 times 1 plus 2x, 1 minus 2x. I would have got this answer quickly or a little faster if I had noticed that I had a GCF of 9 to start with. And you can try this with factoring out the GCF of 9 first and see what you get alternatively. And I'm going to just show this alternative method in the solution as well. In this case, if you recognize the GCF was 9 to start with, you would want to factor out the 9 as GCF. And with this, you would be left with 1 from the first term and negative 4x squared from the second term. And then recognizing this is our new a squared and this is our new b squared. So in this case, you would have a equal to 1 and b equal to 2x, because square root of 4 becomes 2 and square root of x squared becomes 2. And now again, using what we know about the difference of squares, we would have 9 times 1 plus 2x, 1 minus 2x. So this would be really the ideal method for us to go through over here. That way we're working with smaller numbers. And then to solve for the x coordinate of the x-intercept, we can go ahead and do the same thing as before, setting 1 plus 2x to be equal to 0 or 1 minus 2x equal to 0, meaning x is equal to negative 1/2 or x is equal to positive 1/2. So our x-intercepts are going to be 1/2 comma 0 and negative 1/2 comma 0. And that's going to be our final answer for this question. And similarly, the next part, part E, is really the same process. And this time I'm not going to make the same mistake. I'm going to go ahead and check GCF first. So if I look at part E, there is a GCF of 5x that I can take out from both terms already. So I can say m of x, I can factor out 5, and I can also take out the lowest degree of x. And once I have this form, we can actually get 5x minus 3 and recognize that I was wrong and it wasn't difference of squares in this case. And when we have the special forms over here, it doesn't work out to be difference of squares in this particular case because we don't have a variable squared minus a constant squared. And this will be particularly clear once we have this factored form already. Now once I have these two linear factors together, I know I cannot factor any further, and that means I'm done, because in this case I have a second degree term and a first degree term, and that's what stopped me from using difference of squares. And again, looking back to part F, that was a typical difference of square question where we have 9 being a square number and 36x squared being a square number as well. So once we do this, we would want to set each factor to be equal to 0. So 5x equals 0 or 5x minus 3 equal to 0. And here x equals 0 or 5x equals 3, x equals 3/5. Therefore, we get the x-intercepts are 0, 0 and 3/5 comma 0. And this is a good reminder really to make sure that we're being careful when we're going through the process. When I'm going through things fast, I also make mistakes of forgetting to factor out GCF and misrecognizing patterns. But what I said still stands. If you have a binomial, always check whether that's a special form first. That would always be my first suspect, and go from there. Now that we have covered all the special cases for factoring, we can go back to all the trinomials that we can work with for factoring. And for trinomials, there are possibilities that they are still special forms like a perfect square trinomial, but there are also possibilities that we just have to do the AC method as we have been doing before. Now going back to part A, it's a trinomial, and I first want to check whether that's a special form of trinomial, meaning it's a perfect square trinomial. And to recognize perfect square trinomial, we want to check whether the first term and last term are perfect squares. And the first term, 9x squared, we do recognize 9 as a perfect square, so this is a perfect square term. And if this was indeed a squared, that would mean a equals 3x. And similarly, if the last term is truly b squared, that would mean b is equal to 1 over here. And then we want to check whether the middle term is equal to 2ab. And a is 3x, b is 1. We want to check whether that's equal to 6x. we do indeed have 6x equals 6x. So once we recognize this, that tells me that I can go ahead and factor this as a perfect square trinomial. So f of x would be a minus b squared. It's a minus because this is a minus sign in front of the linear term. They do match, and that becomes 3x minus 1 squared. So I don't need to do any AC method, even though the leading coefficient is not equal to 1. And once we have this form to find x-intercept, I just need to set the only factor that's distinct over here to be equal to 0. And 3x equals 1, so x equals 1/3. Therefore, the x-intercept is 1/3 0. And we talked about this before. Whenever you have a perfect square trinomial, you would only have one x-intercept because the two factors are identical to each other. These two x-intercepts essentially overlap, and that's also going to be the vertex of our function over here. And moving on to part C, we have this form. Our leading coefficient is equal to 1, which is pretty nice to work with if we have to do the regular trinomial factoring. And we recognize the last term is 18, which is not a perfect square. And we also recognize there's no GCF to take out at all. Because of this, I know this is not a perfect square trinomial, so I have to use a regular method for factoring. And now to factor it, remember when we have this form, we just want the product to be equal to C, which is 18, and we want the sum of two numbers to be equal to B, which is equal to 9. So we want to find such numbers that multiply to be 18 and add up to 9. Because both product and sum are positive, that means the two numbers I need are both positive. If you go through your factor pairs of 18, you should find out eventually 3 and 6 are what we want. And once we find this, we can go ahead and write this out. Because it's positive 3, we would do x plus 3. And then the other one would also be x plus 6 over here. Now that we have this factored form, we can go ahead and use a zero product principle to find where the x-intercept is. So if h of x equals 0, that means x plus 3 equals 0, or x plus 6 equals 0. And x equals -3, or x equals -6 for this case. And once we have this, we can say that the x-intercepts are -3, 0, comma, -6, 0. Moving on to part D. Feel free to pause the video if you need some time to write down notes or digest all the information, but I'm just moving along in case you already got some of the problems pretty quickly. And in part D, we have this case. Again, it's a trinomial. We recognize pretty quickly 2 is not a perfect square number, so this can't be a perfect square trinomial. And neither is 8. Also, it's -8. So all these signs tell us it's not a special form, and we will have to use AC method because our leading coefficient is 2. It's not 1. So to use the AC method over here, we want to first find out what's our A and what's our C over here. So our product needs to be the product of A times C, which is 2 times -8, or -16. And our sum still needs to be equal to B, which is equal to 5. And in this case, if we would have the two numbers being one negative and one positive, and also we want the sum to be positive. So we need the positive number to have a larger absolute value. And here, if you go through your factor pair options, you will hopefully recognize that we really can't find two numbers that would work out nicely for our case, because 16 only have so many factor pairs. It's 1, 16, 2, 8, or 4 and 4. And none of these combinations will actually give us the sum of positive 5. And this is where we know if we want to do this with AC method, this just doesn't work. And we wouldn't really be able to go through the factoring process anymore. And the very last resort for any factoring problem or for any x-intercept x-intercept problem or quadratic problems, in order to solve for 0, the last resort is always a quadratic formula. But I always want to try the AC method before I go down to the quadratic formula. Even though quadratic formula always works, it's usually not the most efficient method because you're always working with radical and ln expressions overall. So this doesn't work over here. So we would say there's no such integers that would satisfy our conditions over here. And therefore, we have to use a quadratic formula in order to find zeros over here. So AC method doesn't work. And now moving on to quadratic formula, I want to write down the formula one more time. Negative b plus minus square root of b squared minus 4ac all over 2a. Once we do this, we're going to get negative b is negative 5 plus minus square root of b squared, which is 5 squared, minus 4 times a, which is 2, times c, which is negative 8, and then divided by 2a, which is 2 times 2. And altogether, if we keep simplifying this, we're going to get negative 5 plus minus. Under the square root, we have 25 plus 64. And this is all over 4. So 25 plus 64 will be 89, and we're going to just leave it as square root of 89 because it is a prime number. And it's fine, our number is messy. Good thing is we don't have to graph this. So to find or list the x-intercept, we're just going to use these two values. We have negative 5 plus root 89 over 4 comma 0, or negative 5 minus root 89 over 4 comma 0. And these are the results. And this old method of quadratic formula, it works universally, but it's usually not very efficient at all. So save it for last. If none of the other methods work, go to quadratic formula over here. Now moving on to part E. I think the lettering is slightly off. I would fix that later. But for k of x, if we want to factor that, we want to go ahead and check the GCF first again. So once we factor out the GCF, which is 3, we would get x squared plus x minus minus 12 as a result. And this, you can see, again, simplify our question a lot more because we don't have to worry about the factor of 3 anymore. We just need to focus on the part inside the parentheses. And inside the parentheses, we have a trinomial with leading coefficient equal to 1. So with this, we can start with GCF and then work with a case of leading coefficient equal to 1. When leading coefficient is equal to 1, it's nice because we know the final form should look like some x being the first term always, and we want to find two numbers that would multiply out to be negative 12 and, multiply out to be negative 12. So product is negative 12. And we want the sum to be equal to positive 1 because this is a plus 1x. And the two numbers that will work out is going to be positive 4 and negative 3. So we'd have positive 4 and negative 3, and then we're done. So even though the initial leading coefficient is not 1, we can work this out very nicely in this case. And once we do so, we're going to set each factor to be equal to 0. The first factor is technically 3, but 3 cannot be 0. So I'm just going to go to the second one, x plus 4 equal to 0, or x minus 3 equal to 0. Therefore, x equals negative 4, or x equals 3. And the x-intercepts we have are negative 4 comma 0 and 3 comma 0. That's going to be our answer. And last but not least, part H over here, we have n of x being 6x squared minus 17x plus 12. And this is a case where we recognize there's no GCF because 17 is prime. And that leaves us, again, trying the AC method first. If AC method doesn't work, we'll have to do quadratic formula. But let's try AC method first. So to use the AC method, we're going to have two numbers that would multiply out to be the product of A times C, which is 6 times 12, or 72. And we want the sum of these two numbers to be equal to B, which is negative 17. And because the sum is negative and product is positive, that means these two numbers have to both be negative. And that happens in this case. It actually works out pretty nicely. For 72, it has a factor pair of negative 8 and negative 9. They work out. Luckily, we don't have to use quadratic formula. And therefore, we can rewrite n of x for AC method. Remember, we keep the first term, keep the last term, but rewrite the middle term. The two numbers are negative 8 and negative 9, so I'm going to rewrite negative 17 to be negative 8x and negative 9x, and then keep the last term, which is plus 12. And I'm going to just block this information out a little so it's easier to see this whole process. Once we have four terms, we resign back to the factor by grouping. First two to go together, last two go together, connected by addition. First parentheses, the GCF we want to take out will be 2x. That leaves us with 3x minus 4. Second parentheses, because the leading term is negative, I'm going to factor out a negative factor. So plus a negative becomes minus. And the common factor is going to be a constant of 3. Once I factor out negative 3 from negative 9x, I get a 3x left. Negative 3 taken out from positive 12 gives me minus 4. Because I factor out a negative coefficient, make sure you flip the signs of everything inside the parentheses. And once we have this, 3x minus 4 becomes a common factor between the two, and then we have 2x minus 3 left. To find the x-intercept, we are going to set each one to be 0, and 3x minus 4 equal to 0, or 2x minus 3 equal to 0. Therefore, x equals 4/3, or x equals 3/2. Therefore, our x-intercepts are going to be 4/3, comma 0, and 3/2, comma 0, like this. And that's how we can find the x-intercepts for this one. In this case, AC method does work. So just to look over and make sure we know the method to use for each one, this going back to the first one, we use a perfect square trinomial. Then for part B, we used factor by grouping because we have four terms to start. And C, it's a regular factoring trinomial with leading coefficient equal to 1. Part D, we first started with AC method because the leading coefficient is not 1 and it doesn't work out. We don't have integer solutions. As proven by our final answer, we have a pretty messy answer, but we know quadratic formula always works. And part D, we had to use a GCF factoring first, and then we resort back to this leading coefficient equal to 1. Part F, we had a binomial, so we know it's a special form of some sort. In this case, it's difference of squares. Part G, we would have this quadratic form, but we don't have any constant term, so we only need GCF for factoring in this binomial form. And lastly, we have a leading coefficient not equal to 1, and AC method does work out for us. So we have a final result based on that.